Hello, my name is Toby Dunn, and my project is an investigation into the natural mineral lick at Lick Creek. My mentor is Professor George Furniss of the Bitterroot College. When you walk out into this meadow and see the pits that the elk and deer have mined, you can't help but have a lot of questions arise. And to our knowledge, no one has yet tried to answer any of these questions. So looking at this through the lens of geology, the two main questions we wanted to answer are, what is the source of the minerals and what are the types and concentrations of those minerals? Professor Furniss suggested Mazama volcanic ash as one potential source. And as you can see from this 1968 map by Williams and Goals, the Bitterroot Valley is well within the boundary of the Mazama ash fall. So a second potential source is Chalice volcanic ash, suggested by Professor Furniss after personal communications with geologist Jeff Lawn, who's a co-author of a 2001 surficial geologic map of the Bitterroot Valley. So I reviewed this map with Professor Furniss to see how a certain rock layer containing Chalice volcanic ash lies beneath the Lick Meadow area, indicating it as a potential source. And the image on the left here shows a map of the Bitterroot Valley and where we collected those two source samples, Mazama and Chalice ash along Highway 93 there. And this aerial image is of the Lick Meadow, and you can really see from this image what I mean by pits. And when you're walking through this meadow, you can see some really significant observable differences in the pits, and one of the main ones is the soil. So on that north end of the pit, where I have pits 1, 2, and 3, and even pit 4, the soil is much darker, so more organic matter is present, and it's a finer kind of texture and consistency. And you can see different grasses have grown back into the pits. That's why from this image, it's almost hard to see the definition of those pits. But when you progress to the south end of the meadow, towards pit 7, the soil changes. And it becomes more of a granular mix of clay and rocks. And when you dig in, you can see little pockets of a powdery white substance, which would indicate the presence of a salt. And this image also shows the locations of the different, where I dug out the different samples and their corresponding parts per million concentration levels. So this is my method, simple method of testing those soil and ash samples to determine if the soil and ash samples would be leaching into a distilled water solution and how much in a given amount of time. And again, those were measured in parts per million. And this graph shows the results from my testing. So this indicates that there are water-soluble minerals present in the soil and ash samples, and that the concentrations of those minerals are significantly higher in certain samples. And you can also see how, so the blue is for test 1, which was done shortly after the initial mixing of the samples. And then the red is test 2, which was done 24 hours later. And you can see an increase in all of the samples in that amount of time in their parts per million concentration levels. So this is an interesting image from Lick Pit 7. And this is actually the particular spot where I took the soil sample that had the highest parts per million reading. And you can really see from this image how the elk and deer have carved out this bank. And I kind of like to imagine an elk standing there with his tongue out, just licking over and over to get at the salts and the minerals in the soil. So about 2 months after that initial testing we sent 3 of the samples, the one from Lick Pit 7 that had the highest parts per million reading, and the 2 Mazama, or the Mazama ash and Chalice volcanic ash samples off to energy laboratories to determine the mineral composition of those samples. And this table shows those results. So some of the main differences you can see in this table is that Chalice volcanic ash contains several additional trace elements, including aluminum, copper, manganese, phosphorus, and zinc, that are not present in the Mazama and Lick Pit 7 samples. You can also see that strontium is present in Lick Pit 7 and Mazama ash, but it's not present in Chalice volcanic ash. And you can also see that Lick Pit 7's values are quite a bit higher, so they're more concentrated than Mazama and Chalice ash, particularly when you're looking at calcium, magnesium, and sodium. And I will get back to why we think that is shortly. So in this table, we normalized the electrolyte values, those four main electrolytes, calcium, magnesium, sodium, and potassium. And we created percentages so that we kind of better compare the profiles of these particular electrolytes. And you can really start to see how Mazama ash is much more similar in profile in these particular electrolytes to Lick Pit 7 than Chalice volcanic ash. So in particular, if you're looking at sodium, Lick Pit 7 is about 63%, Mazama is 49%, so within 15% of each other, whereas Chalice volcanic ash is quite high at 86%. So that's well above the Lick Pit 7 amount. And then Lick Pit 7 and Mazama have very comparable amounts of magnesium. Chalice doesn't have any traceable amounts of magnesium. And calcium, again, is between Lick Pit 7 and Mazama is within 15% of each other. And Chalice is actually quite low in calcium comparatively at only 10%. So we found further support for Mazama ash as the potential source for the mineral licks from a 1972 map on Pleistocene glaciation in the Bitterroot Range by W.M. Weber. So Professor Furniss explained to me how glacial moraine deposits. So a moraine is the rock that melts out and is deposited as a glacier melts and recedes back. And so these different glacial recession periods, they deposited the moraine and developed a catchment basin that is now the Lake Meadow before the Mazama eruption occurred. So this created a spot for the ash to be contained within that area. And you can see this in the illustration by Professor Furniss, the progression through time and the development of that landscape. So since this meadow is a catchment basin, it also collects rain and snow melt that saturates the ground in early spring, but it dries out over the summer. So this evaporative process would also explain why we were seeing those higher levels of electrolytes in that Lick Pit 7 sample compared to the volcanic ash samples. So in conclusion, we have determined from our initial research that Mazama volcanic ash is a more likely source than Chalice volcanic ash for this natural mineral lick. We've also determined that there are biologically necessary electrolytes present, including sodium, calcium, magnesium, and potassium. And one of the bigger picture things that I find fascinating about this initial research is the progression of events through time. So what I talked about in the previous slide, you have those gradual geologic processes involved in the landform development of the Lick Meadow area, coupled with the catastrophic geologic events with the Mazama and Chalice volcanic eruptions. And because of these processes, there is now a meadow with a natural mineral lick that plays a valuable role for wildlife in the present by providing a biologically necessary source of electrolyte supplementation. So I think that our initial research is compelling enough to warrant additional research and more detailed sampling and analysis of the soil and potential source samples to provide more conclusive evidence that Mazama ash or potentially another source is the source for this mineral lick. And I think that this initial research just kind of starts the conversation about this mineral lick. And I hope that more people join in from different scientific backgrounds to see all what can be discovered from this natural mineral lick. So I'd like to thank my mentor, Professor George Furniss, for all of his time and support and knowledge that he's imparted to me throughout this process. And I'd like to thank my husband, Levi Dunn, for letting me borrow his GPS and teaching me how to use it, and for assisting in preparing those Google Earth images. And a special thank you to the Patty Furniss Educational Memorial Fund for financial support on this project. Thank you for listening.